So this is part one of the Honors Chem Mid-Year Exam Review, and in this review I am not going to have the questions printed up on each slide. We'll just be going over the answers for each question. You have the questions themselves in the packet to refer to or in your book. These are all questions from the book with the exception of a couple of stoichiometry questions that are on the sheet on the front of the practice packet. So just the answers, not the actual questions, will be on each slide. So the first question is number 20 on page 33, and the question refers to a series of measurements and asks to judge whether or not they are accurate, precise, or both. The measurements themselves agree with one another fairly closely, which is the definition of precision. So you can argue how close they have to be to each other to be precise, but these are fairly close enough to be called precise. However, given that the measurements are all below 15% and the actual accepted value is closer to 16%, we would say that these measurements were not accurate. So they can be precise without being accurate. Precision is how closely the measurements agree with each other, and accuracy is how closely the measurements agree with the accepted value. Number 27 is rounding numbers to three significant figures and then converting to scientific or exponential notation. So for A, we have 3.12.54. So for A, we have 312.54. We're going to round that to three significant figures, which would be 313. And then to convert it to scientific notation, I have to move the decimal point to here to get a digit between number between 1 and 10. And in order to do that, I had to move the decimal point two places to the left. So an exponential or scientific notation would be 3.13 times 10 to the second power. B is 0.00031254. So the coefficient, or the number in front of the times 10, is going to be the same. It's rounded to 3.13 times 10, and in this case, in order to get the decimal point from where it started to where it is now, between the 3 and the 1, I had to move 4 places to the left. When you have to, to the right. When you have to move to the right, you make that a negative exponent. So 3.13 times 10 to the negative fourth. C is 31,254,000. So we're going to get the same coefficient again, 3.13. In order to get that coefficient, I had to move the decimal point 7 places to the left, so 3.13 times 10 to the 7th. D, we're going to get the same coefficient for all of these, in case you haven't figured that out yet. 3.13 times 10 to the negative first, because I had to move 1 place to the right. And the last one on this is 3.13 times 10 to the negative second power. So because this was 31.254 times 10 to the negative third, I move the decimal place 1 to the left. I increase the value of the exponent by 1, so it goes from negative 3 to negative 2. So 3.13 times 10 to the negative second power. Number 31. In this case, we're performing a series of mathematical operations, and then we have to round our answers to the appropriate number of significant figures. So in the first answer, we end up with 467.3. And this one's a tricky one because if you look at the operations, we have addition, subtraction, and division. According to addition and subtraction rules, you would focus on the number of decimal places, and all of the numbers have 2 decimal places. However, because we also have multiplication, we have to look at the total number of significant figures, and the smallest number of significant figures in these values is 4. So I have to round my answer to 4 significant figures. So you always have to go with whichever rule gives you the smaller number of significant digits. So that's kind of tricky, but you have to keep that in mind. For part B, we're going to get 0.2 3 0.35. And this is where, like the first one, you've got two different sets of rules because it's subtraction, division, multiplication. We're assuming the 100 is an exact number, so it doesn't factor into our significant figures determination. And in this case, since the numbers in the numerator, which is where the subtraction takes place, have 3 decimal places, I have to round my answer to 3 decimal places, and the other rule would have given me 4 significant figures. So again, I have to round my answer to the smallest number of significant figures allowed by the rules. So you go with whichever set of rules gives you the fewer digits. For part C, we're going to get 326 because some of the values have 3 significant figures, so I have to round my answer there. Part D is going to be 75, again because there are values with only 2 significant figures, so that's where I'm rounding my answer. Part E, we end up with 0.12, and that's restricted by the number of decimal places. For F, we are going to have 0.207. G, the answer rounds to 4.9, okay, because we have values with only 2 significant figures. And for part H, we're going to end up with 0.011 because they have 3 decimal places and we have to round our answer there. So in number 33, we're doing some metric conversions, and a little bit of dimensional analysis goes into this. So we're converting 8.43 centimeters to millimeters. So I know that 100 centimeters equals 1 meter, and I know that 1 meter is 1,000 millimeters. So when I multiply that out, I get 84.3 millimeters. For B, I'm going from centimeters to meters. This is only going to be a one-step problem. And we have 2.41 times 10 to the second centimeters times 1 meter is 100 centimeters. And so we get 0.241 meters. Part C, we're converting nanometers to centimeters. So we have 294.5 nanometers. There are 1 times 10 to the 9th nanometers in 1 meter. And then there are 100 centimeters in 1 meter. So we multiply across the top, across the bottom, and divide those out, and we get 2.945 times 10 to the negative 5th. For D, we're going from meters to kilometers. 1.445 times 10 to the 4th meters, and there are 1,000 meters in 1 kilometer. So when we multiply that and divide, we get 14.45 kilometers. For E, converting meters to millimeters, so 235.3 meters to millimeters when there are 1,000 millimeters in 1 meter. That equals 235,300 millimeters. And the last one on this, F, we're converting 903.5 0.3 nanometers to micrometers. And so again, we know that there's 1.0 times 10 to the 9th nanometers in 1 meter. And then there are 1 times 10 to the negative 6th, no, 1 times 10 to the 6th, sorry, micrometers in 1 meter. Multiply those numbers together, and we get 0.9033 micrometers. So next up we have number 57, which is a question about the density of an object, and we're told that 0.200 grams is equal to 1 carat, and then we're asked to find the volume of a piece that's 5 carats. So if 0.200 grams is 1 carat, then 1.00 grams would be 5 carats. So now we know the mass, and we're told that the density, so we got 1.00 grams, and how many cubic centimeters would that be? And the density is 3.51 grams per 1 cubic centimeter. So when we cross multiply and solve, we end up with 0.284 cubic centimeters would be the volume of 1 gram. Number 67, which is related to states of matter and elements versus compounds and mixtures. So if we just go through the numbers, the Roman numerals for the pictures, the first one actually doesn't apply to any of the descriptions below. It's a gaseous element, and that is not one of the choices. Number 2 is D, which is a mixture of a gaseous element and a gaseous compound. Number 3 is also D, mixture of gaseous element and compound. Number 4 is just a gaseous compound, which is choice A. Number 5 is C, a solid element. And the last one, number 6, is a mixture of 2 gaseous elements, which is choice B. So next we're moving on to page 76, and we're going to start with number 49 on that page, which is a chart. And I'm going to try to redraw the table. I'm not going to draw all the labels for what each thing is, but we have the symbol, the number of protons, number of neutrons, number of electrons, and the overall charge. And then we have to fill in what's missing. So I'm just going to draw the table. Okay, so in the first box we have the symbol, and we're going to give that a 75, atomic number of 33, and that's arsenic. And the next one is 128 and 32, tellurium, and in this case it has a charge of -2. And then we have sulfur, 32 and 16. We have thallium, 81, with a charge of +1. The arsenic, by the way, had a charge of +3. You have to remember that. And then the last one is platinum, 195 and 78. Okay, so to fill in the rest of the numbers, the number of protons in the nucleus is always the atomic number, which is the bottom number on the left when you write the symbol. So 33, 32, 16, 81, and 78. The number of electrons in the third column is the same as the number of protons unless there's a charge. So let's put the ones that have charges on here. plus 3, minus 2, no charge, positive 1, and no charge. So for the ones that are no charge, the number of electrons, so these are protons, neutrons, electrons, and charge, plus or minus. So for the two that don't have a charge, those are easy. The protons and electrons are the same. When there's a positive charge, that means there are fewer electrons. So we take away 3 electrons from 33, we get 30. Negative charge means you have extra electrons, so 34. And then a plus 1 means there are only 80 electrons for the 81 protons, which gives it an overall charge. The number of neutrons is found by subtracting the number of protons from the mass number, which is the number on the top left in this notation. So to fill those in, we have 42, 76, 16, 123, and 117. Number 67 is naming compounds. So to go down the list here, copper 1 iodide, copper 2 iodide, cobalt 2 iodide, sodium carbonate, sodium bicarbonate, tetrasulfur tetranitride, sulfur hexafluoride, sodium hypochlorite, barium chromate, and ammonium nitrate. Number 69 is writing formulas given the names. And so we have, for the first one, we're going to end up with CSBr, cesium bromide, BaSO4, barium sulfate, ammonium chloride is NH4Cl, chlorine monoxide, ClO, silicon tetrachloride, CSiCl4, chlorine trifluoride, ClF3, beryllium oxide, and magnesium fluoride. Okay, moving on to some stoichiometry problems. We've got number 21 starting out on page 123. This is about finding the average atomic mass of an element with 3 isotopes. And the way we find this is we multiply each mass by its percent abundance, and then we add the answers together, however many there are. We repeat as necessary. In this case, there are 3 isotopes that we're working with and 3% abundances that we're going to take into account. So the first one is 78%, almost 79%. The second one is 10%, and the last one is 11%. So when we multiply those numbers, we get 18.9, and so on, and we get 2.49858, and we get 2.8606426. Add those up and you get 24.30501576. With the significant figures, we are going to round that, right, to 24.3050 AMU. And you can see that the weighting of the percentages gets that average closest to the most abundant isotope, whereas if we were just taking a straight average, it would come out very close to 25, since that's right in the middle of the three values. But the percentage weights the average toward the most common isotope. Number 29. Okay, in this case, we're converting from mass to atoms. Okay, we're starting with 0.200 grams, and we want to convert that. We're talking about diamond, which is pure carbon, so 1 mole of pure carbon has a mass of 12.01 grams. And then we're going to multiply that to get to atoms by 6.022 times 10 to the 23rd. That's how many atoms there are in 1 mole. When we multiply that together, we get a value of, when we round, 1.00 times 10 to the 22nd atoms of carbon in a 1 carat diamond. Number 51 asks us a bunch of questions about this molecule, C14, H18, H18, N2O5. The first question is, what is the atomic mass? Well, we multiply the number of each element by the atomic mass for each element, and then we add them all together. So we get 168 plus 18 plus 28 plus 80. When we add those numbers together, we find that the molar mass is 294 grams per mole. Part B asks us how many moles there would be if we had 10 grams of the substance. Well, we just established that 1 mole has a mass of 294 grams. So 10 grams divided by 294 is 0.0340 moles. And how much would 1.56 moles, what would the mass of that be? So we flip over our conversion factor. 294 grams times 1.56 is 458.64 grams. And part D, if we had 5 milligrams, how many molecules would that be? Okay, so this is going to take a couple steps. We go from milligrams, first of all, to grams, 1,000 milligrams in 1 gram. Then we go from grams to moles, 294 grams in 1 mole. And then we can go from moles to molecules, 6.022 times 10 to the 23rd. And we put all that together, we get 1.0 times 10 to the 19th molecules. Part E. If we had 1.2 grams, how many atoms of nitrogen would that be? Well, first, convert to moles. 1 mole, 294 grams. And then there are 2 moles of nitrogen in every 1 mole of the molecule. And then there are 6.022 times 10 to the 23rd atoms in 1 mole. Multiply that out, and we find that there would be 4.9 times 10 to the 21st atoms. Okay, we're still in 51, part F. 1.0 times 10 to the 9th molecules, when there are 6.02 times 10, 6.022 times 10 to the 23rd molecules in 1 mole, and 294 grams in 1 mole. That all mean that if you had 1.0 times 10 to the 9th molecules, you would have a grand total of 4.9 times 10 to the negative 13th grams. And last part on this problem, how much does one molecule of this substance weigh in grams? Well, 1 mole is 6.022 times 10 to the 23rd molecules, and 1 mole is 294 grams. So when we do that out, we find that one molecule would have a mass of 4.9 times 10 to the negative 22nd grams. Number 63, empirical formula. It's 59.9% titanium, which means it's 40.1% oxygen. And so the way we find the empirical formula, we convert the percents to grams. We convert grams to moles. So 1 mole of titanium has a mass of 47.9 grams. 1 mole of oxygen has a mass of 16 grams. We convert those, we get 1.25 moles of titanium for every 2.51 moles of oxygen. Divide both numbers by the smaller number, 1.25, 1.25. And we find that the ratio is 1 to 2, which means the formula would be TiO2. That's the empirical formula of titanium oxide. Number 67, we're asked to find the empirical formula and the molecular formula. So first, we're going to go through the empirical formula, the same process as the last problem. 30.4 grams of nitrogen for every 69.6 grams of oxygen. Nitrogen has a mass of 14 grams per mole. Oxygen is 16 grams per mole. And we get answers of 2.17 moles and 4.35 moles. Divide both by the smaller number. And we get a ratio again of 1 to 2, which means that the empirical formula is NO2. Now that empirical formula would have a mass of 46 grams per mole. We're told that the actual molecular mass is 92 grams per mole. So we divide 92 by 46, and we find that that's a ratio of 2 to 1, which means the molecular formula is twice as large as the empirical formula, so N2O4. That's the empirical, that's the molecular. Okay, number 77, balancing some equations. For equation A, we end up with copper plus 2 silver nitrates yields 2 silvers plus 1 copper nitrate. In the second equation, we have zinc plus 2 hydrochloric acids gives us zinc chloride plus hydrogen gas. And in the third one, we have gold sulfide plus hydrogen, 3 hydrogens, produce 2 gold and 3 hydrogen sulfides. Next one, 79, a bunch more balancing. These are all combustion reactions. So for A, we get 2C6H6 plus 15O2 yields 12CO2 plus 6H2O. B, 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. The third one, we have C12H22O11 plus 6O2 yields 6CO2 plus 11H2O. D, 4 iron plus 3 oxygen yields 2 iron oxides, and 4 iron oxides plus oxygen yields 2 iron oxides. And for the problems that are on the sheet on the front of the packet, these are some stoichiometry problems. For the first question, if we have 1.40 grams of nitrogen, and nitrogen has a mass of 28 grams per mole, nitrogen gas, that means that we have 0.05 moles nitrogen. The ratio of nitrogen to hydrogen in the reaction is 3:1. So that means that we will have 0.15 moles of hydrogen times 2 grams per mole means that we will have 0.30 grams of hydrogen gas that we need for that reaction. For the second question, part A is determining the limiting reactant. And in order to do this, we take the moles of each reactant that we're given and we multiply them by the mole ratio. So for the aluminum, it's a ratio of 2:4 with the product. It takes 4 moles of aluminum to make 1 mole of product, which means that the moles produced by 0.32 moles would be 0.16. And then we do the same thing for the oxygen, and we find that the ratio here is 2:3, which means we would get 0.173 moles from that amount of oxygen. So the answer that gives us the smaller result is the aluminum. So aluminum is limiting. And then the question is how many moles of product would be formed. Well, we kind of already found that answer up here, 0.16 moles would be produced, and then if we had to, we could convert that to grams by multiplying by the mass of the aluminum oxide. Okay, the last question on here, number 3. The first part is to determine how much theoretical yield we could get if we react 6.0 moles of nitrous oxide. Well, if we react that according to the equation, it takes 2 moles of the nitrous oxide to produce 1 mole of product. And so that means we're going to get 3 moles of the product. The product has a mass of 108 grams, which means in theory we should get 324 grams of product. That's the theoretical yield. That's what stoichiometry always tells you. The question says our actual yield is only 61%. So we multiply 0.611 times our theoretical yield of 324, and we find that it would be 197.964 grams that we should get, and we would round that to 200 grams for significant figures because this number has 2 significant figures, and that's how it rounds out. So that's it for the first part of the review. We'll do the solution and gas and redox problems in part 2 coming up.